Okay, so this video is going to be on basic differentiation rules, which is like taking derivatives, but without using the definition of a derivative. So that's what's pretty helpful about this. So the first rule is basically the derivative of a constant. In other words, like any number, non-variable. If you take the derivative of any constant, you're just going to get zero. You could look at that with the definition of a derivative, the f of x plus h minus f of x. If it's a constant like y equals 3, let's say, for example, you know that it's going to be f of x plus h is going to be 3, f of x is going to be 3. The other thing is, because you know derivative is slope, you can look at this graph and look all the way across this right where I'm drawing, and you can realize that like every one of those slopes is 0. So look at those little lines. Those are important. Those are just little snapshots of the graph and slopes. So you can see the slope of that for any number, no variable, is going to be 0. So y equals a number is your function, then you're going to have just a 0 slope. We don't use no slope. We say the slope is 0, so it's flat, horizontal line. The power rule is an important one. So if you have n being a rational number, like a fraction, right? Rationals for ratio. And then you have this function x to some power, right? Sorry about that. And so the n is the rational number, right? You need the function to be differentiable, and we'll talk more about that. We may or may not have talked about differentiability, but you need to be able to take the derivative. And then what's going to happen is you're really just going to bring the power down in front. This is a shortcut to doing the definition. And you're going to leave the x alone, and you're going to subtract 1 from the power. So we can do an example of that. But basically f prime of x, the derivative of f of x, is going to be n, right, x, and then you're going to subtract 1. So you'll bring that n down in front, x to the n minus 1. That's what's happening. So if you had like x to the third, it'd be 3x to the second. So here's x to the third, like we were just talking about. Just write that out. dy dx, another way of saying y prime or f prime of x. And that's going to be 3, bring it down, and then subtract 1 from the power. So this is called the power rule. You're going to use it all the time. It's going to be pretty straightforward. And if you use the definition, you'll still get that. So look back at your definition of derivative problems, and you'll find that this power rule kind of dictated what it would come out as every time. So should be able to check with the power rule. Now, if you ever take the definition of a derivative, you have to take the derivative by the definition. You can check your answer with the power rule, which is kind of nice. In this example, we got f of x equals 2x to the fourth. So you can bring that 4 in front, but that 4 is going to multiply by the 2. So you'll wind up with 8x to the third. So same kind of principle. It's just if you have a constant there, it will multiply by that number. So the 4 comes down in front, multiplies by the 2, and you get 8x to the third. Next, we're going to go to the constant multiple rule, which kind of touches on what we were just talking about. If you have a function that you can take the derivative of, and c is a real number, we're going to use, obviously, real numbers in this course. You can take the constant out and then take the derivative. So anytime you have like a number in front of something that you want to take the derivative of, you can just take the number out in front, then derive whatever you want to derive, and then put the number back. So if you look at like the example we did before, the constant multiple rule kind of holds. You multiply that number after if you want. So if you had 7 pi x to the third, you could take the 7 pi and just leave it alone, and then do the derivative of the x to the third, and then multiply the 7 pi in at the end. So if y equals, then dy dx. Remember, I'm just showing you all the different ways of writing y prime, or this is also known as the derivative of y with respect to x. That's how you read that green fraction. So that 7 pi is just going to like hang out in the beginning. This will save you a lot of frustration in the future. And then you're going to do the 3x squared, and then you'll put that 7 pi back. So you can basically take the 7 pi, multiply the 3, you'll get 21. I think you'll just get 21 pi x squared. So if you notice here, you basically just took the derivative of the x to the third, got the 3x to the second, so that's y and that's y prime. And what you do is you pulled the constant out and then you put it back. This works for constants. You can't do that for variables. And pi is not a variable. Pi is a constant. It's 3.14, whatever. So the rule works for constants only. Do not try to separate x's off and use this rule. It won't work. So definitely a lot of rules that we're going to be talking about here. We're going to get into a couple different ones in just a minute, but try to keep them straight. And I think you'll find that these are actually pretty simple. So sum indifference is the next one. Basically what it means is if you have a bunch of terms, like you're trying to derive something with a bunch of terms, you can just take the derivative of each term and that will be fine. You can just take it, you can take the derivative term by term, if that makes sense. So if we make a long chain of things here, take an example where f of x is equal to 2x squared plus 3x to the third, or the 3 halves actually, because we haven't done a rational exponent yet, minus 7 plus 1 over x. So this is going to be a good problem right here because there's a lot of things going on here. So take the derivative of that. Hopefully that isn't too big of a deal for you. So take all the derivatives separately. 2x squared, you can bring down, you can separate the 2 out, or you can just keep it there and bring down the 2. Either way, it's going to be 4x to the first, which you don't really need to put the first, but it is to the first. Now we look at this one. We got to bring that power of 3 halves down and multiply it by the 3 which is in front. So I think that you'll have 3 over 1 times 3 over 2, because you're going to bring that 3 over 2 out front. You'll have 9 halves x to the, but let's think about that for a second. 3 halves, we have to subtract 1 from that power. So I think we'll have 9 halves x to the 1 half. 9 halves x to the 1 half. So just watch out because right here with the exponent is where people can get stuck. Sometimes they won't really know what to do, right? This minus 7 that we're going to underline in a second here, moving on to the next term. We're just doing term by term. This minus 7 here is a constant, so we know the derivative of any constant, no variable, constant number, is 0. So we could write 0, but we don't really need to. And then we can move on to the next term. So this is 1 over x. If it's like this, ideally you want to write it as a power. If you can write this as a power, you can use the power rule, which is going to make your life infinitely easier. So 1 over x is actually, aka, x to the negative 1. So if you write it as x to the negative 1, you can bring that power down, leave the x alone, and subtract 1 from that power. Of course, now you're subtracting from negative 1, so you'll have negative 1x to the negative 2. So even though you're still just subtracting 1 from the power, just happens that you're subtracting from negative 1. So you're going very negative. So this is your answer. In the book, they're going to ask you to like rewrite the problem, then derive it, then simplify. So you see that AKA, that's an example of rewriting the problem. Then you've derived it. That's the second line here where we get all these answers. And now simplifying. Well, you shouldn't have negative exponents or complex fractions. Those are the two things I don't really allow when you're simplifying. You don't need to have common denominator or beautiful looking problems, but you can't have a negative exponent or a complex fraction, a fraction inside of a fraction. So this must be changed over to negative 1 over x squared. So that's what has to happen when you simplify. Other than that, those are really my only 2 rules for simplifying. So don't go crazy simplifying. Making root x is nice because x to the 1 half is root x, but it's not necessary. And just to reiterate, f prime of x and y prime are kind of meaning the same thing here, okay? So there's that problem. Definitely getting to be, a little bit more moving parts here, but not too bad. Just go term by term and follow the rules. Okay, so next we're going to get into just a couple of trig functions. So I want to talk about sine of x. And if you were going to derive sine of x, this is something we could probably memorize at this point. These two you're really going to want to memorize. The derivative of sine of x is cosine of x. Do you see there's a prime there on that f So it says f prime of x. It's not very visible on the video here. So the derivative of sine of x is cosine of x, and the derivative of cosine of x is going to be negative sine of x. So we're going to look at some graphs for that, but that's what I want you to kind of just understand. These two derivatives are really important, so just memorize them, and we'll deal with the rest of the trig functions later. The other thing I'd like to mention about this is that the derivative of sine is cosine, so you'll notice that um, sine goes up and down, like it has a positive slope and a negative slope over and over, and cosine has a positive value and a negative slope over and over. So looking at slopes of sine and values of cosine might kind of help you to get an understanding. We should definitely look at a graph. So here's a graph. So um, okay, sorry. So I'm narrating this just in case you didn't know. I'm narrating over this video after I recorded it because the audio wasn't good. And so I thought I was going to show you that graph, but maybe not. Okay, so the next one we're going to talk about is e to the x. E to the x is derivative is e to the x. Remember, those primes are there. You can't see them very well. So we'll look at that in a second, but first let's just go through a quick example with the negative sine of x here. So let's go through this example where we have y equals 2x to the third minus 3 sine of x. And let's just try to figure out if we can do that term by term. So look at the first term, which is 2x to the third. You know that y prime for that is going to be 6x squared. And then if you look at the next term, this is where that constant multiple rule comes in. See the negative 3? You can just leave that alone. So you write the negative 3 down because it's a constant, nothing happens with it, and you focus on the sine of x. So the sine of x, you memorize the derivative to be cosine of x. So you've just replaced sine of x with cosine of x because you're deriving it, and you get this for an answer. So that's an example of that one. Next, we're going to talk about the e to the x one. So let's say we have a negative 3 e to the x. Well, the derivative of that is you can leave the negative 3 because it's a constant multiple, so it stays. And then you derive e to the x. But the derivative of e to the x is e to the x. So there's not really a lot to do with this. The derivative of negative 3 e to the x is in fact negative 3 e to the x. Another way that you can do this, you'll see that I wrote up here, I wrote negative 3 and then I wrote e to the x in brackets. Sometimes that's what I do. I pulled that negative 3 out and I'm just leaving it alone. You see how I arrow it down? Then I'm deriving e to the x, and derivative of e to the x is e to the x. Sometimes these square brackets are going to be helpful. We'll use that for some notation later. We'll use d dx. So soon we'll do the other trig functions. Focus on memorizing sine's derivative is cosine of x, and derivative of cosine is negative sine of x. Watch out, that can get confusing. And then we'll deal with logs and other exponents like 2 to the x later. So for now, we're just going to bite off one chunk of this whole issue. Last thing I want to talk about is a horizontal tangent line. So I just want to talk about this problem here, x to the fourth minus 8x squared plus 2. And we want to find where this graph has a horizontal tangent line. Okay, so if this is y or f of x, whatever we want to write it as, we need to derive that. Because the tangent line's slope, right? I like to think of it this way, okay? I'm going to give you an analogy here that I've tried to teach myself. I've tried to remember to say. The derivative is not the slope of the tangent line. I know I'm going to say that 100 times, but remember that the derivative is not just the slope of the tangent line. The derivative is the slope finding function. It's the function that finds the slope of the tangent line. So that's why it's a function. It changes. The slope of the tangent line is always changing. So it's kind of like I think of the analogy of a fish finder, the slope of the tangent line finder. And you just plug in an x value to find that slope. So what's happening here is we want to look at where these slopes are 0, right? Because that's where we're going to have a horizontal tangent. So these are all the horizontal tangents. I'm drawing them in. If I can find, right, these are all m equals 0, these little tangent lines, these spots where I wrote in those tangent lines, if I can find what the slope of the tangent line is and set it equal to 0, I could find all those little points that I drew in there. Now note that this graph doesn't necessarily match the function here, x to the fourth minus 8x squared plus 2, but it's just to help you visualize what's going on here. So what is the slope of the tangent line? Well, the slope of the tangent finder, the slope finding function, just like a fish finder, is 4x to the third minus 16x. So what we need to do is if y prime is the slope finding function, we need to set y prime to 0. If we set the slope to 0, we can then look and solve, find x's that give us those green lines that you're looking at on this graph. So if y prime is a function, right, with an x in it and all that, and it comes out as 0, then that's going to be the place where these green lines are happening. Those are going to be the x values where these green lines are happening. It's pretty important. We need to find an x, y where these lines are horizontal. So why don't we just solve when the slope is equal to 0? And that will tell us all those green lines. Maybe there are a few of them, maybe there aren't so many. We can factor this. We take out a 4x, we got x squared minus 4x, or just 4, sorry, equals 0. And then we have 4x, and then we have x plus 2x minus 2. All that equals 0, set each factor. So we got x equals 0, x equals 2, and x equals negative 2. My apologies. Those are going to be the three places where this function, the black function, has a horizontal tangent line. And if by chance we were to graph the derivative, which is a whole nother story, okay? So don't mix up original function with derivative. That's a very common misconception to have. But if we were to graph the derivative, we would find that it crosses the x-axis at all those points. It's 0. So this is kind of what we will be getting into, trying to find horizontal tangent lines. It's a pretty big topic in calculus, definitely something you want to know about. So remember, you're finding the derivative, which is the slope finding function, then setting that to 0 and finding the x's, the places where that happens. Now, if you were going to say the point where it happens, you really should have the x and the y. So what you would do is you'd put in these x's, 0, negative 2, and positive 2, and get the y's. But would you put them into the green circled equation or the red equation? You'd put them into the green one, right? So what we'll do now is we'll just kind of graph this quick. So give me just a second here. Okay, so here's what I did. I went ahead and made that graph. It took me a while to find the window, but eventually I got there. And this is the graph of the green circle, okay, not the graph of the derivative. And you'll notice a couple of places. Why don't you look at where x is 2, where x is negative 2, and where x is 0? I've drawn in red lines. If you go to an x value of 2, you have a flat spot, right? And when you go to x is equal to negative 2, you also have a flat spot. And when you go to x equals 0, you have a flat spot. We need to know the y values because they did say find the point, right? So we should have y values. But we don't want y prime values because you know what? The y prime values are obviously going to be 0. So we just need to find these 3 points. We have all the x's, and we need to take a second and find the y's. So plug into the original function, the green function, to find the y's on the original function. Because if you plug into the derivative, you're going to keep getting 0. I think that's pretty much it, so we will wrap it up there. I'll see you in the next video. Peace.